3, are we live? We're live. It's Wednesday. We're in Washington, D.C. I'm Tom Siebel, and it's a great honor to share some thoughts with you about what is going on with the intersection of developments in information technology, communication technology, and the grid. Okay, so I'm a computer scientist. I trained at the University of Illinois. My field was relational database theory, and I've been in the information technology business now. This is my 4th decade, and the game all began at Bell Labs with the invention of this device by John Bardeen and William Shockley, and things have moved pretty quickly since then. And this is, this story that kind of covers the last 70 years, I think, is pretty well documented in this book called The Innovators by Walter Isaacson. If you haven't read it, I recommend it. So Shockley goes to Silicon Valley, and we have Shockley Semiconductor, and then Fairchild Semiconductor, and then Intel, and of course we all know about Moore's Law. And so we don't need to talk about that, except that it has dramatically driven down the cost of computing, perhaps by a factor of 3 almost every year. And there's some question as to whether or not we're reaching some physical limitations there. I would argue that it doesn't matter, okay, because the cost of computing and storage is right now is a falling knife, okay, with the advent of the elastic cloud, okay, and we're seeing computing infrastructures and storage capacity, the power of which none of us could have ever imagined. And so here we are, it's in 2017, and we look at what are the big vectors driving innovation that are going on, in this century. Well, clearly we have cloud computing, we have new social human computer interaction models, associated with what you have in your left front pocket. The advent, this new field of big data, which is hugely important. People think big data is about the size of the data set. It is not. Okay, big data has to do with, is independent of the size of the data set. It has to do with the fact that you're dealing with all of the data rather than making inferences from a sample. Okay, and it is a completely different computational model, and we're able to solve problems that were previously unsolvable. And the final vector is, basically, we come out of the dark ages of AI and we can do something useful with machine learning. And I think machine learning is an incredibly exciting field. This is a field where I think the cell has divided maybe 4 times, and what will happen in the next 20 years will change absolutely everything. Now, if we look at the confluence of all of this, okay, this all collides with this vector that's happening and commercially, globally associated with this field that we call, technically you call the cyber physical systems, popularly known as Internet of Things. Okay, and this is a vector, a trend that is undeniable in its scale. Okay, rough numbers at the beginning of this century, there were perhaps 500 million sensors installed. And today there are 19 billion. Today, in 5 years, there will be 50 billion sensors installed. We are censoring every value chain, so the devices are becoming remotely machine addressable, whether this is consumer packaged goods, travel and transportation, aerospace, healthcare, government services, or the grid. So now, we have spent the past, say, 8 years and about $250 million building a technology platform, a platform as a service that allows organizations to build, design, develop, deploy, provision, and operate large-scale cyber-physical systems. And this basically is in the area of the Internet of Things. Now, if we look at the rate at which these sensors are being deployed across value chains, we see actually the first value chain to be censored is the grid. And so this is where we began. And the value chain, to belabor the obvious here, so give me 120 seconds to be pedantic. This value chain, as it exists at the beginning of this, you're going to time me? Okay, fine. Okay. You let me know when it's up. So this value chain, as it exists at the beginning of this century, is largely as it was drawn up by Thomas Edison and George Westinghouse. At one end, we boil water. Okay, we rotate a turbine, rotate a magnet through a coil, generate a current, step up the voltage to high voltage, step it down to medium voltage, get to a meter at 440, and then to a consumer. Now, in response to this, underneath these systems of generation, transmission, distribution, kind of metering and consumption, the information technology community has responded with these what I'll call second generation enterprise information systems, usually built on top of relational database technology that do useful things. Things like Siebel Systems that does CRM, or SAP, customer care and billing, or work order management, or voltage control, or whatever it may be. And there are SCADA systems, and they all serve useful purposes, but because they're the second generation enterprise information systems that we all come to know and love over the last 3 decades, we know that they tend not to want to share data for lots of important reasons. I don't know if they're important reasons or not, but there's lots of reasons why it's very difficult to share data. Now, this value chain is going through an upgrade this decade, of which this audience is well aware, where all of the devices in the value chain are becoming upgraded so that they're becoming remotely machine addressable. People are focused on the smart meter, and yes, we are deploying 1.6 billion of those worldwide between now and 2023. But it's not simply the smart meter. It's the home thermostat, the variable speed fan at Walmart, the meter, the step-up transformer, the step-down transformer, reclosers, capacitance banks, phasor measurement units, vibration sensors on nuclear reactors, rotational velocity sensors on water pumps, vibration sensors on water pumps. It's all being censored. The amount that's being invested this decade globally to upgrade this value chain from the grid to the smart grid is $2 trillion. Well, let me help you out. That's a lot of dough. And for those of you who, and I think there are a few here in the room, who are around in, say, 1993, 94, 95, when we commercialized the internet as we know it today, I can assure you nobody was thinking about spending $2 trillion. This is happening, it's budgeted, and it's being spent. Now, when you censor this value chain, so we obviously have below the line, these technologies have been driven by the benefits of Moore's law, and but above the line we have, to go backwards, okay, above the line, this begins to look like a fully connected, maybe I get this to go backwards, one more time. That's what I want, okay, thanks. This above the line, this begins to look like a fully connected sensor network. And some of you will remember, and many of you know personally, Bob Metcalfe, okay, who at Xerox PARC invented this thing called the Ethernet, turned out to be pretty useful, and coined this, what became known as Metcalfe's law, where he says the power of this network is a function of the square of the number of devices on the network. So what we have where IoT meets the grid, okay, and this is what the smart grid is all about, is kind of a collision of Moore's law and Metcalfe's law. And so we went about building, we spent, again, 8 years and $250 million developing a platform that would allow a grid operator to aggregate, and let me just say one other thing, it's obvious to everybody here that the data, when we censor these value chains, the amount of data increases by some orders of magnitude. If we read a meter once a month, that would be 12 times a year. If we read it every 15 minutes, that would be 32,250 times a year. There's 4 orders of magnitude. By the time we have PMUs on transmission and distribution lines, we look at these guys putting out signals that say 60 hertz cycles. We're now at like 9 orders of magnitude. So the data acquisition rates are breathtaking. So the objective was, we looked at this as when people think about energy efficiency, I would say in the last 10 years, particularly in the United States, they look at the endpoints of the grid. They think about either one, changing the source of fuel from hydrocarbon to non-hydrocarbon-based fuel sources to boil water, or secondly, they're looking at energy efficiency measures to figure out how we could get people to turn out the lights. To the tune of, we spend, I think, $10 billion a year, okay, in 39 states to get people to turn out the lights 1%, use 1% less energy a year. Okay? The real opportunity is to optimize the entire machine, to look at the machine, and we can do this by looking at it as a cyber-physical system. So what we do is we've developed a platform that allows the grid operator to take the union of, this is the same slide turned sideways, okay, to take the union of the operational data, the union of the sensor data, the union of data from the extranet, weather forecast, social media, what have you, and aggregate those data into a unified federated image. And then develop a platform, a cloud-based platform, horizontally, elastically scalable platform, to allow us to provide platform services like access control, security in motion, encryption in motion, encryption at rest, batch processing, map-reduce processing, stream processing, iterative processing, and data science services to optimize this grid infrastructure. And so the idea was to do that, to deliver a family of applications that allows us to increase the efficiency of the value chain by, say, 30% and reduce the greenhouse gas impact by order of 50%. And these applications do things like fraud detection, predictive maintenance, grid resilience, cybersecurity, customer churn, generation management. I'm gonna give 2 examples. And now we've deployed these systems at about 23 enterprises around the world, most of which are utilities. And I'm gonna talk about 2 specific examples. I'm going to talk about Enel, and I'm going to talk about Engie. Okay, those 2 utilities together are roughly the size of the United States. Okay, so Enel has 60 million meters. Okay, Engie has roughly 30 million meters. There's 100 million meters in the United States. So let's take the Enel use case. Here, we've taken Spain and Italy, where they have 42 million smart meters installed. There are 50 million smart meters installed in Europe today, okay, as so far. And what we did, we aggregated 7 years of data from all of their legacy information systems, the 42 million meter sensor network, meter data management, customer care and billing, work order management, network topology, what have you, 2 different SCADA systems, the 42 million meter sensor network, and we go to the extranet for social media, weather, terrain. We aggregated those data. This is 10 trillion rows of data into a 750 terabyte data image. It grows at 300 gigabytes a day. We process transactions and apply machine learning algorithms at the rate of 1 million transactions a second. 1 million transactions a second. Okay, and the benefit to Enel is in basically 5 areas. First, revenue protection, fraud identification for Spain and Italy. We can tell them, we have machine learning classifiers that tell them who's stealing energy, how they're stealing it, and how much are they stealing. Predictive maintenance for their distribution assets. Predictive maintenance for 65 gigawatts of conventional generation, predictive maintenance for 10 gigawatts of renewable generation, and then customer churn. This is the largest IoT application in production on the planet Earth. The economic benefit of this application today is 261 million euros a year in recurring economic benefit. Okay, fully deployed across the stack, fully deployed across the Enel infrastructure for 60 million meters in 40 countries. The economic benefit is order of 7 billion euros a year in recurring economic benefit. Now let's look at Engie. Engie is roughly an 80 billion euro integrated energy company, oil and gas, natural gas, LNG, gas distribution, LNG terminals, electricity distribution. Okay, here we're building 28 IoT applications across 24 lines of business. Okay, smart cities, B2B, B2C, M2M across the entire enterprise. The expected economic benefit from this application is 1.5 billion euros a year. And we have built a center of excellence that consists of C3 IoT personnel and NG personnel to deploy these applications. We're bringing 2 production applications live every 6 months for the next 5 years. So this is the largest IoT production effort going on the planet Earth today.
My name is Yves Legélard, and I'm the Chief Digital Officer as well as the Group CIO of ENGIE. The energy sector is at a defining moment, and digital.
Looks like we might not make it, huh? Am I live? Am I quiet? It is. Anyhow, it's a very, very exciting project where we're bringing the CEO is a physicist by the name of Siebel. Okay, she is unbelievably smart. Before I leave this subject, so what we've done now, we're automating utilities. Well, I mean, we do them in the United States too. Exelon, Baltimore Gas and Electric, Commonwealth Edison, Eversource. But I would say that from, we work in China, we work in Japan, we work in Europe, we work in the United States. Quite candidly, okay, the United States, as it relates to grid automation, is not even in, if China is by far leading the world in the use of information technology for grid automation, Western Europe is close behind, okay, then it would become Japan, okay, and the United States is like in 100th place. They're not even in the game, okay? And I think it has something to do with the regulatory infrastructure in the United States, but honestly, they're not even in the game. Now, new page, okay, I want to talk about something else, another part of my life. This is a philanthropy called the Siebel Energy Institute, and we'll be holding our board meeting on Friday, and then we'll have a meeting on Saturday, on Sunday at the National Academy of Sciences. The Siebel Energy Institute, this is a 501c3. All of the work goes into the public domain. This is a multinational initiative. It's headed up by Shankar Sastry, who's the Dean of Engineering at UC Berkeley. Many of you know him. I think maybe he used to run DARPA. This is a joint effort with Tsinghua, École Polytechnique, University of Tokyo, Politecnico di Torino, MIT, Princeton, Carnegie Mellon, University of Illinois at Urbana, Stanford, Berkeley, and I probably forgot something, okay? And we are working to basically advance the science. We have industry partners who are very active in this, okay? And we are providing seed funding for people to write proposals to advance the science of machine learning for cyber physical systems, and they've been to date mostly focused on energy. We basically provide funding of $50,000 to $100,000 for people to write their grants, whether this has been smart cities, grid cybersecurity, Volt VAR, behavioral systems, predictive analytics, whatever it may be. And so we basically fund people writing their proposals, and now they've gone on and gotten millions of dollars of funding from the governments in the UK, DOE, NSF, MEDI, whatever. The current grants awards will be given out Friday. Okay, and this is mostly focused on smart cities initiatives, cyber physical data analysis, human decision-making, energy infrastructures, next generation of traffic management. We're also we'll be then holding a conference at the National Academy with 400 scientists around the world about grid cybersecurity. And the next call for papers will be about grid cybersecurity. I think this is a very important topic. If you have not read the book Lights Out by Ted Koppel, I recommend it. Let's see if this video will work.
Successful cyber attacks happen on an almost daily basis in the US. No industry is immune to being hacked. The electric grid is no exception. Without power, critical infrastructure, including telecommunications, sanitation, transportation, and healthcare shut down. A simultaneous attack on only 9 substations could trigger a near nationwide power outage. Repair or replacement of damaged equipment could take weeks, months, or even years. Drinking water becomes scarce. Generators run out of fuel. Supermarket and pharmacy shelves go bare. Emergency food supplies are exhausted. Cell phones, portable radios, and flashlights lose power. Modern medical care ceases to exist. Americans are thrust into a way of life they are ill-equipped to survive. There are no sufficient measures in place to help the U.S. avert or recover from this kind of disaster.
National Academy, we're gathering 400 scientists from the National Academy, at the National Academy on Friday, Saturday, and Sunday to discuss this topic. We'll be putting out a call for papers about grid cybersecurity. I think this is a critically important issue. Our purpose in so doing is to elevate the dialogue and get this topic on the agenda. It will be, people who will be participating in this. The moderator will be Ted Koppel. The keynote will be given by Bob Gates. Okay, we will have industry executives, scientists from every place from Tsinghua to the University of Tokyo to Ecole Polytechnique to MIT and Princeton. Mike Hayden will be involved, Richard Clark, Tim Conway, Bob Lee, Director of Security Symantec. This is kind of broken into 2 sessions. One, what's the nature of the problem? How frequently are these grid incursions happening? How vulnerable is the grid? Okay, it's highly vulnerable in my opinion. Okay, how hard would it be to take it down? Not hard. Okay, and then the second subject is really exploring, what sort of research needs to be done to secure this type of critical infrastructure? What do we need to look at? Is it AI? Is it blockchain? Where do we need to go? And so we're going to encourage research in that area and then put out a call for papers. I can tell you that so we're doing these cyber physical systems today in energy systems, in healthcare, in aerospace, in travel and transportation, in government services. And it's basically all the same problem, but I think one of the most critical problems relates to the grid infrastructure. I can tell you that this has been of the various challenges. These are very, very challenging problems. The data sets are staggering. The data processing requirements are staggering, but by far the most. But I think we are getting to the point where we can trivialize that. We've trivialized the data aggregation problem, which was not that long ago, not very trivial. But I think the part that is non-trivial and is going to remain non-trivial for the next couple of decades relates to the data science, the machine learning, the deep learning, the neural networks, and the development of the data science. This is where we will make the sparks fly. I believe we will be human capital constrained there for quite some time. It is again, I played the game of information technology for a few decades now, and this is by far the most interesting, by far the most challenging, and by far the most meaningful. So ladies and gentlemen, Thank you for the courtesy that you've extended to me this morning. It's a great honor to have the opportunity to address you. I know that you're all involved in very, very important work. To the extent that you see that there's an opportunity to collaborate with us, I am Siebel@siebel.org. I'm very easily found, and we'd be happy to collaborate with you. So thank you for the courtesy that you extended to me this morning.